Structural geology focuses on the various types of geologic structures and the interpretation of their origin. Different plate tectonic settings include stresses that may produce a range of these structures that can be generally described as either brittle, faults, or ductile, folds. We will review the principal types of stress, tension, compression, and shear, and the various types of geologic structures that occur as a result. This is a view of the spectacular fold exposures developed in the Paleoproterozoic Maverick Formation in Barnhart Canyon, located in the Mazatzal Mountains of central Arizona. Here, the white, tightly folded quartzite layers contrast with the reddish-brown slate and form what are called chevron folds. The deformation that formed these folds occurred during the Mazatzal orogeny over 1 billion years ago. Understanding stress and strain is central to describing and interpreting geologic structures. Simply put, if rocks are subjected to stress, they may be deformed and thus show strain. Stress and strain, cause and effect. For example, these flat-lying sedimentary rocks at the top of the South Kaibab Trail in the Grand Canyon are relatively undeformed or unstrained. However, if they are subjected to compressional tectonic stress, over time they may be deformed and show strain. These formerly flat-lying sedimentary rocks in Namibia have been deformed into an overturned fold. In the Grand Canyon, the South Kaibab Trail descends through the so-called layer cake formed by the more or less horizontally oriented Paleozoic strata, and starts at Yaqui Point, progresses down through Cedar Ridge, Skeleton Point, and the tip-off on its way to the Inner Gorge, where it then crosses the Colorado River at the Black Bridge on its way to Phantom Ranch. The south rim of the Grand Canyon is underlain by the Permian Kaibab Formation, and in this area forms the edge of the Coconino Plateau, which is part of the much larger Colorado Plateau. Across the Colorado Plateau, including places like the Grand Canyon, the geology is largely characterized by relatively flat-lying Paleozoic and Mesozoic sedimentary units that have not been significantly deformed since their formation millions of years ago. Only locally have these strata been deformed into folds called monoclines. This layer cake stratigraphy and the high desert climate produce spectacular landscapes, plateaus, mesas, and buttes. This is the lower Ugab River area of west central Namibia. And here, the late Proterozoic Quieseb Formation represents a considerable thickness of folded metamorphic greywacke. These rocks represent a late Proterozoic deep-sea fan system that was deformed during the Cambrian collision of the Congo and Kalahari cratons. The region displays evidence of 4 phases of structural deformation, from open folds to tight to isoclinal folds. There are 3 basic types of tectonic stress: tension, compression, and shear. This diagram shows the three basic stresses and their effects on geologic layering. This diagram shows the basic tectonic settings where these stresses dominantly occur. The first situation shows horizontal layering where the rocks have not experienced any tectonic stress and thus no signs of strain. In the next example, compressional stress includes opposing forces that cause rocks to shorten horizontally and thicken vertically. This is the dominant stress at convergent plate boundaries where tectonic plates are moving toward each other. And you can see that on the right. Tensional stress includes opposing forces that cause rocks to lengthen horizontally and thin vertically. This is the dominant stress at divergent plate boundaries where tectonic plates are moving away from each other. You can also see that in both diagrams on the right. Shear stress includes opposing forces moving in opposite directions. This is the dominant stress at transform boundaries where tectonic plates are moving side by side past each other. And we can see that in the bottom diagram on the right. There are two basic types of strain, brittle and ductile. Three factors that control the type of deformation include the temperature of the rocks, the strength of the rocks, and the rate at which the rocks are being strained, also known as strain rate. Faults are geologic structures that represent brittle deformation. Brittle deformation typically occurs in rocks at lower temperatures, at more shallow levels in the crust. Stronger rocks also tend to deform in a brittle fashion. Finally, a relatively fast strain rate typically results in brittle deformation. Folds are geologic structures that represent ductile deformation. Ductile deformation occurs in rocks at higher temperatures, found at deeper levels in the crust. Weaker rocks also tend to deform in a ductile fashion. Finally, a relatively slow strain rate results in ductile deformation. Note, ductile deformation is often referred to as plastic deformation. Not that it has anything to do with real plastic, though. A structural geologist identifies geologic structures in the field. Strike and dip are measurements that describe the orientation of geologic structures, whether it's bedding, foliation, fault planes, fold axes, etc. To do this, certain aspects of the deformed layers need to be measured, typically with a special compass known as a Brunton compass. Dip is pretty easy to visualize. For it, we note the direction of dip is a compass direction, northeast, northwest, southeast, southwest, and the amount of dip from horizontal, 0 being horizontal and 90 being vertical. Al is measuring the dip of bedding at a tilted sandstone outcrop. Not sure what the dip direction is here, somewhere off to the right, but it looks like the dip angle is about 30 degrees from horizontal. Strike is the compass direction of the line formed by the intersection of the feature, whether it's bedding or foliation or whatever, with an imaginary horizontal surface. It's a little more abstract to visualize than dip, so it helps that the strike direction is always 90 degrees or at right angles to the dip direction. So if you know the dip direction, you can easily figure out the strike direction. Susan and Lisa are measuring the strike of bedding of the Shinnerump conglomerate in St. George, Utah. Once the strike and dip are measured, the two measurements are combined and written something like this: north 35 east, 30 southeast. North 35 east is the direction of strike, and 30 southeast is the amount and direction of dip. This information is crucial in documenting deformed layers and geologic structures so that we can identify the geologic structures, make structural interpretations, construct geologic maps, etc. Faults are deformational features that are essentially fractures with differential offset. Faults form under brittle conditions from any type of stress, tension, compression, or shear. There are three basic types of faults, with offset that may be oriented anywhere from vertical to horizontal. They can also occur at any scale, microscopic to mountain-sized. Here, a small fault with millimeters of offset is present in the Estrella Gneiss at South Mountain in Phoenix, Arizona. This fault is located along California Highway 178 at Resting Springs Pass just east of Death Valley National Park. This fault has a few meters of offset. And finally, the mighty San Andreas Transform Fault, here seen in the Carrizo Plain area, has over 500 kilometers of offset and is also the boundary between two different tectonic plates. Resting Springs Pass is located in the Mojave Desert near the Nevada-California state line. Along California Highway 178 near Death Valley National Park is a spectacular road cut of 9.5 million year old welded tuff. The black layer there is part of the welded tuff, as is the cream-colored unit. Several normal faults offset the tuff, with west side down displacement. Dip-slip faults are ones that have vertical offset along the dip of the fault plane. We can identify a dip-slip fault in just a few steps. Once the dip-slip fault is located, we can describe the part above the fault plane as the hanging wall. In really big fault systems, this may also be called the upper plate. Accordingly, the part below the fault plane is the footwall, or lower plate in big faults. Hanging wall and footwall are older terms, originally derived from underground mining operations. Ore bodies and their associated mining tunnels are often located along fault planes. In the tunnel, a miner can hang from the rocks above their head, thus the term hanging wall, and the rocks at their feet are part of the footwall. Once we have identified the hanging wall and footwall, we need to find matching features on either side of the fault, commonly a distinctive bedding layer. From looking at the offset layers, we next determine which way the hanging wall is moved, up or down, relative to the footwall. In the example here, the distinctive dark layers have been offset up on the hanging wall side. This enables us to more precisely name and interpret this fault, which we will talk about next. It should be noted that in many cases it is very difficult to find matching features on either side of a fault, so other means may be necessary to identify the fault. Normal faults are dip-slip faults where the hanging wall is moved down relative to the footwall. These faults are caused by tensional stresses. The dip angle of most normal faults is greater than 45 degrees and commonly 60 degrees or more. These high-angle normal faults typically form where the crust is cold and extensional rates are low. Normal faults are common at divergent plate boundaries, rift zones, and other extensional areas. At left is a small normal fault exposed along U.S. Highway 191 near the entrance to Arches National Park in Moab, Utah. At middle is a high-angle normal fault located in Guatemala. And at right are a series of small normal faults exposed in Mosaic Canyon in Death Valley National Park. Located along U.S. Highway 191 near Moab, Utah, many high-angle normal faults are visible in this road cut, all formed from the same tensional stresses. Here we are at the northwest end of the Moab Valley, in the area around the entrance to Arches National Park. Looking southeast, down the axis of the Moab Valley, toward the Colorado River, Moab, and the La Salle Mountains beyond. The broad valley resulted from salt intrusion in Paleozoic and Mesozoic time, and subsequent collapse caused by groundwater dissolution of the salt cap. The Mesozoic and Paleozoic sedimentary rocks have been arched up into a broad anticline that has been cut by the Moab Fault, a large normal fault over 30 kilometers in length. Displacement of this fault is as much as 2,600 feet, east side down. Vertical movement along the fault is not due to normal tectonics, but salt tectonics, from the presence and movement of thick deposits of buried salt of the Pennsylvanian Paradox Formation. Groundwater dissolution of the Paradox salt is responsible for most of the displacement along the Moab Fault. The Moab Fault is largely buried beneath Quaternary surficial sediments, but is exposed in the area across from the entrance to Arches National Park. Here, the Jurassic Navajo and Entrada sandstones form the landscape around the park's visitor center, whereas older rocks are exposed in the cliffs to the west. This definitely means there's a fault in the area. US Highway 191 more or less follows the trace of the Moab Fault here. Exposures of the main fault and the west branch of the Moab Fault are located just west of the visitor center and across the highway. Several small normal faults are well exposed in the outcrop along the highway. Notice that the west side down movement sense on these smaller secondary faults is opposite that of the main fault, which is east side down. These are called antithetic faults, common in areas of normal faulting. Graben and half-graben are geologic structures common in extensional areas and rift zones. The Basin and Range province of the western United States and northern Mexico is a wide rift that includes many of these structures. A graben is what we call a structural basin, bounded by normal faults on either side. The word graben itself is German for ditch. So if you really want to play the part, you can pronounce it graben. The hanging wall drops down relative to the footwall, often with little or no tilting. The resulting lower area, or graben, typically fills with sediment eroded from the bordering mountains in the footwalls. Indeed, these footwall mountains are called horsts, German for heap. The Basin and Range gets its name from the geology of these grabens and horsts. Many of the mountain ranges in the region are exposed footwall horsts, and many of the basins are located in the graben areas. A half-graben is a structural basin with a normal fault only on one side. This is analogous to a trapdoor. The normal fault in a half-graben typically forms above a curved or listric fault. This causes the hanging wall rocks to become tilted towards the normal fault. Both graben and half-graben can form in the same areas. This is a view of some very distinctive layering with small but extremely well-preserved faults, forming a graben structure, and this is exposed near Zahan, Iran. Some normal faults have dip angles less than 45 degrees, and commonly less than 30 degrees. These are known as low-angle normal faults. The hanging wall, or upper plate, is commonly broken into numerous fault blocks. And since a low-angle normal fault is typically curved, or elliptic, movement along the fault causes rotation of the hanging wall blocks, usually tilting them in the same general direction, toward the fault plane. Large low-angle faults are also known as detachment faults, and are generally master faults with significant horizontal displacement. They are found in areas where the crust is relatively hot and the extensional rate is high. Low-angle faults are also common in large landslides, and serve as the glide plane or décollement for the landslide mass. A great example is the 1998 Mission Peak landslide located north of San Jose, California. This is a low-angle normal fault, or detachment fault, exposed in the Buckskin Rawhide Mountains of western Arizona. Metamorphic core complexes are large extensional features, first described relatively recently, in the early 1980s. These tectonic structures form during rapid crustal extension of relatively hot crust. As movement proceeds along a large detachment fault, the upper plate breaks up into separate fault blocks that rotate with continued extension. As the upper plate becomes progressively thinner, the deeper crustal metamorphic crystalline rocks of the lower plate begin to rise and eventually become exposed. Thus, a metamorphic core complex is formed. Geologists like P.J. Coney, George Davis, and Steve Reynolds mapped and described these extensional tectonic features, first recognized in the Basin Range province of California and Arizona. Significant localities stretch from the Santa Catalina Mountains of Tucson to the South Mountains of the Phoenix area, to the Buckskin Rawhide Mountains of western Arizona, to the Whipple Mountains of southeastern California. This is a simple Steve Reynolds cross-sectional sketch of the South Mountains Metamorphic Core Complex. The South Mountains Detachment Fault is the main low-angle normal fault here. The South Mountains themselves represent the crystalline igneous and metamorphic rocks of the lower plate that have now been exposed by extension. Bell Butte, Tempe Butte, the Papago Buttes, etc. are the exposed parts of the rotated tilt blocks of the extended upper plate. Reverse faults are dip-slip faults where the hanging wall is moved up relative to the footwall. These faults are caused by compressional stresses. The dip angle of most reverse faults is greater than 45 degrees and is commonly 60 degrees or more. These high-angle reverse faults typically form when the crust is cold and the convergence rate is low. Reverse faults are common at convergent plate boundaries, including subduction zones and continent-continent collision areas. The image at left here shows several small reverse faults formed in glacial sediments near Oshkosh, Wisconsin. At right is a small reverse fault related to the Monument Fold in the Ells Chasm area along the Colorado River in Grand Canyon National Park. In Titus Canyon of Death Valley National Park, Jeff describes a small reverse fault to our group. Some reverse faults have dip angles less than 45 degrees, and commonly less than 30 degrees. These are called thrust faults. These faults form when the rate of tectonic convergence is high and involve an upper plate moving up and over a lower plate. And thrust faults commonly accompany the formation of folds. Thrust faults are common at convergent plate boundaries. In some mountain belts, known as fold and thrust belts, tectonic compression creates a complex network of faults and folds. Typically, a basal master thrust fault forms and serves as the glide plane or décollement for the upper plate. These master faults can have significant horizontal displacement. Smaller reverse faults and thrust faults commonly extend upward from the basal thrust into the upper plate. Classic fold and thrust belts are found in the Rocky Mountains and Appalachian Mountains of North America, the Alps, the Zagros Mountains of Iran, and in China, to name a few places. This is an example of a super well-exposed thrust fault at Katobe Knob in the San Rafael Swell area of central Utah. In the image on the right, note the human for scale. Strike-slip faults are different from dip-slip faults in that shear stress causes mostly horizontal movement along the strike of the fault, not the dip of the fault. Strike-slip faults are usually nearly vertical, so there's really no hanging wall or footwall. Two varieties of strike-slip faults can be defined by the relative movement between fault blocks as seen from either side of the fault. A right lateral strike-slip fault is one where the opposite side of the fault moves to the right. The San Andreas Fault in California has a right lateral movement sense. Conversely, a left lateral strike-slip fault is one where the opposite side of the fault moves to the left. The Piqiang Fault in northwest China has a left lateral movement sense. Strike-slip faults are common at transform boundaries, and strike-slip faults that form the boundary between two tectonic plates are known as transform faults. These commonly offset mid-ocean ridge segments. The Piqiang Fault is a northwest trending left lateral strike-slip fault in the Piqiang thrust belt in northwest China. This area lies between the Tian Shan Mountains to the north and the Taklamakan Desert to the south. This strike-slip fault is more than 70 kilometers in length and may have originated as a normal fault in the Permian, but was reactivated as a strike-slip fault during the Middle to Late Cenozoic, related to the Himalayan orogeny. The rock units of note here include the older cream-colored Cambrian to Ordovician marine limestones, greenish Silurian marine sandstones, and the top of the sequence is made up of reddish Devonian fluvial sandstones. The San Andreas Fault is a famous example of not only a strike-slip fault, but also a transform fault because it forms the boundary between two tectonic plates, specifically the Pacific and North American plates. At right here is the Wallace Creek area of the Carrizo Plain in south-central California. This is the Wallace Creek area of the San Andreas Fault. It's a rather famous locality that shows the offset along the fault. Right lateral offset is about 430 feet here at Wallace Creek. During the 1857 magnitude 7.9 Fort Tejon earthquake alone, the San Andreas Fault here moved about 30 feet. Oblique-slip faults are those with some significant component of both vertical and horizontal movement. These faults may be difficult to discriminate from dip-slip and strike-slip faults. Their identification largely depends on having good exposures along the fault. A joint is a geologic structure represented by a fracture where no offset has occurred. Multiple parallel joints make up a joint set, which commonly form in massive, compositionally homogeneous rocks. For example, the slick rock member of the Entrada sandstone is a massive sandstone in Arches National Park. This unit hosts a dominant joint set that is eroded into prominent fins and even arches in some locations. This is the Salt Valley area of Arches National Park. Here, Mesozoic sedimentary rocks were long ago arched up into a northwest trending anticlinal structure due to the movement of the deeper paradox formation salt mass. Subsequent dissolution of the salt along the crest of the anticline formed normal faults and created the Salt Valley Graben. The Mesozoic rocks along the flank of the anticline are highly jointed as a result of the salt tectonics. Seen here from right to left are the reddish rocks of the slick rock member of the Entrada sandstone and the cream-colored Moab member of the Curtis Formation. Folds are deformational features that form under ductile conditions, and mostly from compressional stress. There are many different types of folds, each distinguished by its shape and orientation. Folds can occur at any scale, from microscopic to hand sample, outcrop, and even mountain-sized. A couple important parameters are used to describe the geometry of all folds. The fold axis, also called the hinge line, is the line that trends along the greatest curvature of the fold. The axial plane is an imaginary plane that goes through the fold axis and splits the fold into two equal parts, called limbs. The axial plane may be vertical, horizontal, or inclined at any intermediate angle. The recumbent fold shown at lower right, this image is one of my favorites. Important parameters that describe different folds are the orientations of the axial plane and the fold limbs. Axial plane orientations can range from vertical to inclined to nearly horizontal. Accordingly, the dip of each fold limb changes as well. In an upright fold, the axial plane can be vertical, with the fold limbs symmetrically dipping away from the axial plane. An inclined fold is one where the axial plane is slightly inclined, with the forward limb having a steeper dip than the other. As the axial plane starts to tilt over, the forward limb becomes steeper and steeper until it becomes vertical. An overturned fold is one where the axial plane exceeds a certain tilt angle, causing the forward limb to pass through vertical and become overturned. A recumbent fold is one where the axial plane is essentially horizontal, or laying down. Another parameter that describes the shape of a fold is its tightness, controlled by the angle between the fold limbs. The differences in fold tightness are readily apparent in this figure of upright folds. Gentle folds are broad folds that have 180 to 120 degrees between fold limbs. The limbs of these folds dip gently away from the axial plane. Open folds are common folds that have 120 to 70 degrees between the fold limbs, which dip more steeply away from the axial plane. Closed folds have 70 to 30 degrees between the fold limbs, which dip even more steeply away from the axial plane. Tight folds have 30 to less than 5 degrees difference between fold limbs, which dip, again, even more steeply away from the axial plane. And finally, isoclinal folds have less than 5 degrees difference between the fold limbs, which are essentially parallel to each other. The geometry of a fold can be quantitatively described in the field. Measurements like strike and dip of the various layers help to define the type of fold. A geologist typically uses their Brunton compass to measure the orientation of the layers and important structural features. One basic type of fold is the anticline, where the fold limbs dip away from the axial plane. Block diagrams like this are great for showing folds, both in cross-sectional view from the side and in map view from the top. In cross-section, an anticline points up or forms a frowny face. In map view, the layers of an anticline dip away from the fold axis on either side of the fold axis. An anticline map symbol may be drawn along the fold axis. It has arrows pointing away from the fold axis in either direction to denote the dip direction of each fold limb. Also in map view, you can look at the ages of the different layers to tell what kind of fold you have. An anticline has the oldest layers exposed in the center of the fold along the fold axis, and the layers get progressively younger away from the fold axis in each direction. Another basic type of fold is the syncline, where the fold limbs dip toward the axial plane. In cross-section, a syncline points down or forms a smiley face. In a map view of a syncline, the layers dip toward the fold axis on either side of the fold axis. The syncline map symbol may be drawn along the fold axis, and it has arrows pointing toward the fold axis to denote the dip direction of each fold limb. Also in map view, the youngest layers of a syncline are exposed in the center of the fold along the fold axis, and the layers get progressively older in each direction away from the fold axis. A plunging fold is one that has a fold axis that is not horizontal, but plunges downward. This produces outcrop patterns that are curved in map view. For plunging anticlines, the plunging fold patterns close or point in the direction of plunge. The map symbol for a plunging anticline is the same as an anticline map symbol, with the added arrow pointing in the direction of plunge. For plunging synclines, the fold pattern opens in the direction of plunge and conversely points opposite the direction of plunge. The map symbol for a plunging syncline is the same as the anticline map symbol, with an added arrow pointing in the direction of plunge. In cross-section, plunging folds can look similar to non-plunging folds, but some views can actually show the plunging layers. Monoclines are one-limb folds that have horizontal beds above and below the fold axis. These folds are typically created by movement along underlying faults that deform the overlying layering. The map symbol for a monocline has a line following the fold axis with the added arrow pointing in the direction of the downwarp. The Raplee monocline is a world-class monocline exposed along the San Juan River in southeasternmost Utah. Located along the San Juan River in southeasternmost Utah, Raplee Ridge displays world-class monoclinal folding along its western flank. The sedimentary rocks exposed here include the Pennsylvanian Hermosa group, forming the deepest exposed rocks in the core of the monocline. These are overlain by various members of the Rico Formation and the Algaito Formation redbeds and the Cedar Mesa sandstone. These layers are horizontal along the ridge crest and then dip as much as 40 degrees through the fold until dips flatten again at the bottom. With the Mexican Hat syncline located to the west. This fold formed as a result of the compressional tectonics of the latest Cretaceous to Eocene laramide orogeny, where movement along deep-seated reverse faults caused monoclinal folding of the overlying Paleozoic and Mesozoic sedimentary rock. Structural domes are large circular upwarps that are essentially equivalent to circular anticlines. Like anticlines, structural domes point upward in cross-section. In map view, the oldest layers are located in the center and dip away from the center in all directions. The map symbol for a structural dome has 4 arrows pointing outward away from the center of the fold. The Black Hills of South Dakota are located in the center of a structural dome. Indeed, Mount Rushmore is carved into the Precambrian rocks exposed at the core of the structure. Here are the Black Hills of western South Dakota and eastern Wyoming. This structural dome was formed during the latest Cretaceous to Eocene laramide orogeny, and is cored by Archean and Paleoproterozoic igneous and metamorphic rocks, covered and surrounded by progressively younger Paleozoic, Mesozoic, and Cenozoic sedimentary rocks. Laramide Eocene intrusions are also present, including at Devil's Tower. Mount Rushmore is carved into the Harvey Peak granite, which has an age of 1,700 million years. This coarse-grained muscovite-bearing granite is host to the 60-foot-high presidential sculptures carved between 1927 and 1941. If you ever wondered, this is the view the fellows have to the east, toward the Great Plains. Structural basins are large circular downwarps that are essentially equivalent to circular synclines. Like synclines, structural basins point downward in cross-section. And in map view, the youngest layers are located in the center and dip toward the center from all directions. The map symbol for a structural basin has 4 arrows pointing towards the center of the fold. The state of Michigan is more or less centered on a large structural basin. We end with a summary of the major fold types, including block diagrams of a non-plunging anticline and syncline, a monocline, a plunging anticline, and a structural dome and structural basin. Well, that's all for now. Till next time.